So now I'll introduce the last speaker, who's Alyssa Goodman from the Harvard-Smithsonian Center for Astrophysics. Ben Schneiderman, our fearless leader, and I were discussing about what I should talk about here. And in the end, we chose this title, okay, The Road from Exploration to Explanation and Back. What does that mean? That means that data exploration and tools for data exploration have historically been separate from beautiful data visualizations that you see in the popular press. And what I'd like to show you is that does not have to be the case, and that really the coming together closer of art and science and technology is making that less and less necessary and certainly less and less desirable. So I'm going to be able to show you some of the tools that Manisha and Jeff just showed you in action, and I'm going to give you mostly astronomy examples, but not completely astronomy examples, I promise. And let's just start this way. Let's say we have these two worlds of exploration and explanation, and the road normally in visualization and art goes this way. Okay, you start out with scientists exploring their data, and they work sometimes with artists, sometimes on their own, to explain what they find to the public in these very beautiful visualizations, some of which you've seen today. And that's usually called public outreach. But as I've written here, traditionally the road going in that direction, if it's boring and dry, is called scholarly publishing. And if it's very beautiful, is called public outreach. So I'm going to address both of those today. We'll start with outreach in a bit and then scholarly publishing. But what I'm most interested in is also going the other way and going both ways. Okay, so it's much harder to go this way, from explanation to exploration. And Manish just showed us a very nice example where there are charts already on the web, and you can extract information from them and play with them. And I'll show you another example of that in a little while. And like I said, my long-term goal is to have two-way street, and I think a lot of people here would agree that what you really want is to bring those two worlds much closer together and not even notice that the road is there. Okay? So let me show you one quick example. If I can take you to Vienna, Austria. Don't worry, I'm not calling somebody. I forgot to set the timer on myself. Okay? So in Vienna lives a very good friend of mine whose name is João Alves, who happens to be the director of the observatory there. And João and I share a deep interest in data visualization and in unusual ways to get people to collaborate in person. And he and one of his postdocs, Jan Froberg, hosted a meeting a couple of years ago called Orion Unplugged, which was partially online and partially in person. And during the online part, those of us who were there in Vienna in person, these, by the way, are pictures of the Vienna Observatory and activities at this meeting, but we were sitting around talking about the slides of someone named John Bally, who you'll see on the next slide in a minute, who is the world's expert on the internal structure of the Orion Nebula, something that you saw in Curtis's talk before. And we professional astronomers who were gathered around, the ones in person, not the ones online who weren't listening to us, had no idea what the three-dimensional picture of the Orion Nebula in this world expert's head looked like, even though he had shown us data visualization after data visualization after data, but they were so complicated and laden with information that we could not figure it out, but we wanted to suck the information out of his brain. Now, you might notice that the woman, Amy Stutz here, who's an astronomer who's sitting under the telescope, is knitting in this picture. This is from the second part of the meeting after everyone gathered in person, and we decided that rather than just making crazy blackboard charts like at a classic collaborative meeting, we were going to make something better. Why is she knitting? She's knitting because what we decided to do was take a cue from Felice Frankel. Some of you may know her work on image and meaning and picturing to learn, who lives very much at this art-science boundary, and go get a bunch of craft supplies and see if we could engage the 35 experts at the meeting in building a three-dimensional model out of yarn and balls and sticks. And what's funny is that this is going to look kind of funny to you or to the serious scientists here, and it's not very good art, okay? But it's kind of an amazing representation of the Orion Nebula. And the crazy thing is that the otherwise very traditional and serious scientists at this meeting. This was part of a so-called unconference where there was no schedule. This was the ongoing unconference session every single day that the most people wanted to go to. We had to turn people away because they had this kind of opportunity that they don't normally have. In a moment, I'm going to show you that one of the people there even composed harp music based on radio interferometry techniques in astronomy as an ode to Orion, which actually plays in the background of a worldwide telescope tour that I'm not going to show you all of. I'm just going to show you a little piece of to give you an idea. If I slide this movie around, what you can see is that these stars and the pom-poms are in exactly the right place, and all of the other wavelengths that you can't see with your own eyes, but you can see in yarn, line up exactly with the actual structures that are there in the multi-wavelength view of the interstellar medium that you heard about from Curtis. And I'll just give you a little taste. I don't know if that sounds like Orion to you. But anyway, Scott Wallace, who wrote that piece of music, could come here and explain it to the musicians among you. And just so you know, there was a scholarly paper published about Orion, partially as an outcome of this meeting. It's boring and dry, but no, it's fantastic. I'm a co-op, it's fantastic. But what you see here is actually a video of the two world's experts, Joao Alves, our host, who I mentioned, and John Bally, the one who showed the slides we didn't understand, which, by the way, it's okay if this is on video. We told him we didn't understand them. And here they are looking at the side view of that model and explaining to each other what's going on. And you can Google this and look up the Vienna model of Orion on YouTube, and you can see the whole thing. Okay, but let's return for a moment to the world where people have to play by the normal rules, and they don't get to have craft supplies. Okay, so I told you that I would cover these two examples of going that way, from explanation to exploration, the public outreach one and the scholarly publishing one. In both of them, the goals are the same, to find new ideas and make new discoveries. Okay, but let me start with public outreach. So here, from just a couple of days ago, how many people are familiar with the Astronomy Picture of the Day website? If you're not, that might be the most valuable thing I mentioned. So set that to your home screen, and every day you can have some beautiful image or movie about space. And this one caught my eye a couple of days ago because I remembered I know the scientists who made this picture, and I thought, this is actually from a while ago. And so I went and looked it up, and so this is just from 2 days ago, but in fact there was a press release from the Hubble Space Telescope in 2015 that had that image oddly oriented a different way because it fit better on a portrait mode than a landscape mode. There is no absolute orientation in space, it doesn't really matter. But my point here is, how would you go from this very public-facing explanation to finding data and exploring it on your own? How hard is that? Many, many years ago, this would have been, not even many, I shouldn't say many, 5 years ago, this would have been somewhat difficult. Right now, it's only a tiny bit difficult, but it's very possible. So if we start in the land of explanation, and we want to go to the land of exploration, what do? Well, we know to go to this Hubble Heritage website because it said Hubble Heritage on the press release. We click a special button where it says Behind the Images, and then it tells me, an astronomer, all kinds of information about what filters were used. And then I know to go to something called MAST, which is the archive at Space Telescope, and I can find that particular data by searching on the name of the source or on some of the other information that is in that table behind the press release. And then, from there, I actually can ingest the data into a program called GLUE, which allows for the kind of interactive, high-dimensional data visualization that Jeff was just telling you about, and I'll talk more about GLUE in a moment. But once I get there, I, as a scientist, can go ahead and explore the data however I like. And I know that we're in Washington, and I'm only supposed to talk about American things, but I should mention that there's a whole other path you could go through a beautiful new program called ESA Sky, that comes from Europe, that oddly enough then points back to the NASA facilities, the MAST archive, and believe it or not, emails you the data and expects you to FTP it. But you could still put that into GLUE. And by the way, I tried all of these things. They do actually work. Okay, so what is GLUE? And what does it have to do with this road? What you see here is the starting point and ending point of the road that I just showed you. And I promise you that if you really know what you're doing, it only takes 5 minutes to drive down that road, which I find pretty impressive. Okay, but what is glue? I'm going to show you a 1.5-minute video that's sort of meant for a slightly nerdier crowd than this. So I'm happy to explain it at the end if you don't follow, but I hope that you will appreciate its value. It's narrated by Tom Robitaille, who's the lead developer for this project. And again, before I play it, let me just tell you, for those of you who are interested in specifically the technology, what this is a Python desktop application that I'm going to show you in a few minutes. Doesn't have to be a desktop application, but its purpose is linking together views of high-dimensional data, or multivariate data, as Jeff called it a minute ago.
Glue is a program for data exploration and visualization that allows users to better understand the relationships that exist within and between data sets. The main interface of Glue provides different data viewers. In this example, the viewer on the left shows an astronomical image of a region where stars are currently forming, and the two viewers on the right show a scatter plot and histogram derived from a separate catalog of stars in this region. The viewers support interactive selection of data subsets, and selections are automatically propagated to other data viewers. In this example, the selected stars are shown in red in all viewers. One of the main features of Glue is the ability to link together different data sets using linear or nonlinear mapping functions. In this example, we have linked the image and catalog data to make it possible for the stars to be shown on top of the image. Three-dimensional data viewers are also available. In this example, we can see the 3D distribution of all earthquakes recorded around the world in the last 6 years. The points are colored by the depth of the location where the earthquake originated. The lighter colors show earthquakes that occur deeper in the crust. This viewer also supports highlighting of selections made in other viewers, as well as direct 3D selections. Glue is designed from the ground up to be a multidisciplinary tool and allows users, for example scientists, to develop plugins to support particular data formats or data viewers. This example shows a volume rendering visualization of medical data that consists of braid scans. We have used Glue to overplot two different datasets, and we can interactively explore this data in 3 dimensions. Finally, Glue is written in Python and makes it easy to interact with the data and subsets using a built-in IPython terminal. For example, we can define new subsets programmatically and have these be automatically highlighted in the interface.
Before I go on, I just want to point out one of the names in the bottom here is Michelle Borkin, whose beautiful medical visualization Jeff showed you in the previous talk. So Michelle was a student with us at Harvard, and one of the goals of Glue was to be able to make the kind of bespoke visualization that she made just on the fly very easily. And Glue is about at the point where we can do that. Okay? So again, the goal here of that kind of work is to just facilitate this two-way traffic. And Ben asked me to include a couple of examples of things we've learned from this kind of work. And so without giving you a whole big long astronomy talk, I'll show you a messy screenshot of how Glue is actually used. And I'll tell you just a very quick story about how you go from a castle in Bavaria using things like Glue and Worldwide Telescope to understand the structure of our own galaxy, the Milky Way. So the extraordinarily quick version of this story without any graphics is we were all sitting around in a meeting where people are locked up for a week to only talk about one subject. It's called the Ringberg Conference, run by the Max Planck Society. And we were supposed to be talking about something else. And someone showed a picture of a weird molecular cloud, little long stringy thing in space at a funny orientation. And someone else in the audience, Andy Burkert, said, "Is that thing parallel to the galactic plane?" And actually no one knew because we had on our blinder vision and we were only looking at the one thing. So we pulled open Worldwide Telescope that Curtis showed you before. We took a look and we found out that in fact this cloud is incredibly parallel to the galactic plane and that we're looking at it in a direction somewhat like what you see in this video. and that having clouds like that, these little long, stringy 300-to-1 aspect ratio things all over the Milky Way, lets us trace out the structure of the galaxy in which we live. It's a much longer story than that, but it basically relies on being able to open software that lets you get to all this rich data just like that in seconds, and having a group of people, experts at this meeting, be able to just collaborate live on the data. So a lot happened since then, but I'm not talking about that today. I'd like to also tell you that you can get an FBI file like mine if you buy an antenna and put it on the roof of the Harvard College Observatory to monitor airplane traffic over Boston. And this is perfectly legal. That's the antenna there on the roof of the observatory. It costs $100 with the Raspberry Pi. And then you can take data from there and just put it straight into software like Glue and investigate all kinds of things about, did you know that when planes land, they only go straight, and when they take off, they veer off to the side? You probably noticed that on a plane, but what you can see in that purple and green visualization there is the difference between the landings, which are purple, and the takeoffs, which are green. Anyway, an amateur can do this, and the reason it's called citizen science on this slide is because those antennas are actually networked together, and if you buy one, you become part of a citizen science network, which has better data about airplanes than you can buy commercially for the whole country. Okay, so now I told you about the sort of public outreach side. Let me talk a little bit about the scholarly publishing side of going, again, from explanation to exploration. So let me explain this diagram first, which occurs in this paper of the future that Curtis mentioned, that I'll get to in a second. What it's about is how people think and how people communicate. So you could say almost creativity at the top and collaboration at the bottom. Okay, but people use all of these different modes: data, pictures, language including math here in science. And in traditional scholarly publishing, the data aren't included at all, and the language and the pictures are separated from each other, as in see figure 4, at the back of the paper. There's not a lot of interweaving of those things. Okay? But ideally, what you would want is for all three of those things, one of which, the data, is usually absent from scholarly publications at all, to be integrated. And so the American Astronomical Society asked Josh Peak, who's a friend of mine, and I to look into what could be possible, and we wrote a very formal report, but we also wrote this fake thing called the Paper of the Future, which has never been published anywhere except this online platform called Authoria that I'll show you in a moment. But really what I want to emphasize is how Galileo, 400 years ago, had this all figured out, and then we messed it up for a really long time, and now we're trying to fix it. So what do I mean by that? I'll show you a little bit of a worldwide telescope tour about Galileo and the moons of Jupiter in a moment, but if you just even look at that top image here in the corner, you'll see it bigger in a moment, and you'll see that what Galileo was able to do was just make these diagrams of Jupiter and its moons interwoven with the text as he was writing the paper. Well, when you got to the Philosophical Transactions of the Royal Society, in 1665, let me just go back here for a minute, that wasn't possible anymore. The sort of typesetting they were using and the formal rules, that didn't happen anymore. And then by the time you get to 1895, where the most prominent scholarly journal in my field was formed, the journal looks exactly the same as it did in 1665, and until very recently, it still looks exactly the same. I'll show you what we did in 2009 to embed some interactive figures in a PDF in Nature, but the Galileo part has to do with this infamous Paper of the Future, and we'll come back to D3 in just a moment. Okay, so these are Galileo's hand-drawn notes, his cleaned-up notes, and his final published drawing of Jupiter and its moons, which at the time he didn't know were moons. And I don't have time to explain the beautiful typography story of those three panels to you, but instead what I'm going to show you is what we could do in Worldwide Telescope. We could take the typeset version of his observations and superimpose them at different times. And so again, this is part of a much longer thing. You can go Google Galileo's New Order, okay, but I can show you the moons of Jupiter going around Jupiter and then superimpose his drawings, and then I can also let this play and show you Jupiter from above in 3 dimensions and explain what Galileo was thinking when he saw only this edge-on view and pictured what must be going on. But importantly, he put his pictures right in the text along with the data, which were so simple that they were essentially the pictures. Okay, and so people don't usually do that now, but it is very possible using the technologies that you saw a few minutes ago to do that. And so let me just show you two examples in this paper. Just for those of you who care, this is a figure where if you click on it, you actually get the Python code running in the browser to make that figure and change it as you wish. But this is the one I wanted to show you. So this is a little story in something very amusingly called D3PO that uses... Yes, I know, we are so funny. That one is on Josh Peak. Uses D3 to visualize the discovery of various moons of Jupiter. So this group here in the 1600s, that was from Galileo. And if you go here, you can see their mass, and you can choose other moons. And each one of these things is a little caption that changes over time telling you this story. But then you can go ahead and not look at the preset view, but explore on your own. And then I want to show you one more demonstration here. This is an image. One of the projects that Laura Trui, who's going to talk tomorrow about citizen science, might mention is something called Astronomy Rewind, where not only are we able to take charts out of papers the way that Manish was showing you that. Could you all please stop using the internet so that this demonstration will work? Okay. Okay. And so you'll see what I did is I clicked on that image, and now that image, which is from 1918, went right back on the sky where it goes. I think we'll turn off the constellation lines, and you see there we are in Worldwide Telescope. There's an optical image of the sky. Let's say I wanted to put an infrared image of the sky in the background instead, and I want to see how that compares to that, and maybe I want to know where I am, and so I could open that same finder scope that Curtis showed you. So the Astronomy Rewind project that Laura may or may not mention tomorrow is doing that for every image in all of the astronomy journal, and citizens are involved. So some of it is automatically done, and some of it is people marking up the captions of the images, etc. So that kind of thing is possible now, and I think we should really do it. Another thing that's very possible is to embed the kind of visualizations I was showing you before directly in papers. So this is something we did quite a while ago now, and let me just skip to the good part. So here's the figure that uses the same kind of dendrogram, by the way, that Michelle Borkin used in the medical paper. And if you click here where it says click to rotate, right in the PDF of the Nature paper, you can interact with the data. And you can also, I'm not going to show you the full demonstration, but you can turn things on and off and basically have a pretty limited but a volume visualization right there in your browser. Okay, so what you really want is not to rely on somebody installing desktop software. If you're really going to have the paper of the future, you want people to just be reading the paper the way they normally would, which these days in science is online, and you want them to be able to explore things just like that, like I showed you a minute ago. So right now, the reason that GLUE is slightly different from the other kinds of Tableau and Vega and other Spotfire, Ben's invention many years ago now, the business analytics tools, those do something called information visualization, where you're looking at mostly ASCII tables of numbers. In science, the field that in the visualization world gets called scientific visualization, we're interested in the interaction between the imaging data, the heart valves that you saw before, and the statistical plots at the same time. Okay? And so we can do that now thanks to this community effort, which is GLUE, which is itself also an open source program. And now we can do it on the web. So here is just a little screenshot from something that we are doing now, where we've put it in the browser working in something new called Jupyter Labs. Okay? And then what you can do is you can actually publish an entire paper in something called Jupyter Notebook, which is an online version of Python. And in fact, just to tell you the truth, that Authoria program where I showed you the paper of the future is just running on something called GitHub, which is something scientists use to collaborate on code. So these worlds of technology and science and art are all really starting to merge. Okay, so what is it? This is almost the last thing I want to say. What is it that's really enabled all of this? I think if you look here, let's have another little n-gram view, and let's look carefully at the last several years. You'll notice that the word collaboration has surpassed the word creativity. And what makes this all possible is collaboration. And I just want to look at a few aspects of that and then conclude. So one of the first times I met Manish, I showed this funny box. Has anybody ever seen this toy? This is called snap circuits. Okay, so it's a way to make electronic circuits where there is very elegant pre-made little resistors and capacitors, and they all just snap together, and it's so much easier than, say, soldering. Okay, although I really like soldering. I inhaled a lot of lead as an undergraduate. But anyway, okay, so you have this idea of a kind of plug-and-play world, and that's what a lot of open-source software lets you do. It lets you plug one thing into another. I didn't show you very carefully, but when I showed you that Nessie demo, one of the things, Nessie is the name of that big cloud that lets you study the Milky Way. Anyway, one of the windows there was itself Worldwide Telescope running on the web, plugged into this Python program, which was surprisingly not difficult. But I'll also tell you that glue doesn't always work perfectly. So all the code is online. And even people like me who are quite involved in the project can use the online platform of GitHub to complain about the code and collaborate by complaining, as we say. And so this is a long post I made about how the axis labels on this plot were wrong when I started to make the plot to show you today in the talk. Hopefully it's fixed by now. Somebody can go check. Okay, so these are two different collaborative platforms that have to do with code. And then the reason I'm showing you the banner for the annual visualization meeting is if you look very carefully, it says VAST, InfoViz, and SciViz, which are three different visualization communities. One visual analytics, one information visualization, and one scientific visualization. And I think that even those three communities, which to those outside any of them don't seem like they should be separate, are finally coming together. And again, the point of software like Glue is that you can have a statistical plot, what would traditionally be called a scientific visualization, right next to a statistical or an analytic plot, and have them interact with each other. What we need now, of course, is some more design and artistic input to make these things look better so that people will want to look at them. And then last but not least, let me just mention the Zooniverse that you'll hear a lot about tomorrow in the citizen science world. And this is the logo of the project I mentioned, Astronomy Rewind, where citizens are helping mark up all the images so that you can revitalize them by turning them back into data instead of just raw images. And then you, again, because of this modular nature and this collaborative spirit, you can see them in any program you like, including Worldwide Telescope. So again, what I really want is for this to be a two-way street and for it to be really short, and all of these organizations are helping make that possible. And if anybody is going to be in Cambridge on March 20th, you're welcome to attend our annual so-called Seamless Astronomy Party, where all of the people who work on software like this gather and drink green beverages this year. So anyway, thank you very much.